In episode 1, we talk about word embedding basics and the simplified version of attention mechanism. So before I dive deeper into what actually happened for attention mechanism, I want to talk about another essential concept for a transformer, that is position encoding. Let's step back a little bit. So before transformer, the most popular model for natural language is LSTM. So I want to spend some time to talk about it. LSTM is a recurrent neural network. So a traditional RNN has a single hidden state that is passed through time, and that can make it difficult for the network to learn like long-term dependencies. LSTM model solved this problem by introducing a memory cell. This is a container that can hold information for an extended period. So it makes LSTM like capable of learning long-term dependency in sequential data. So it works great at that time for language translation, speech recognition, and like time series forecasting. So on the right, there is the LSTM cell. However, there's a problem with it. So LSTMs are slow and less efficient than transformer due to their sequential nature, which means the training phase, we need to pass the sequential data one at a time. Okay, now let's jump to transformer. On the right-hand side, there's the transformer architecture. I'm not going to dive too deep into that one in this slide, but you can see it is very different from the previous LSTM. Transformers can capture global dependencies more effectively in long sequence compared to LSTM and others like GRUs. And as a result, transformer is better at parallelizing compute. Intuition is, for example, in episode 1, when we have a sentence, we don't have to pass in one word at a time. We actually pass everything as the input embedding at once, right? So it makes the calculation a lot more effective. And if we can parallelize the computation, it scales up a lot better than LSTM. Of course, there are like other stuff that makes transformer works, and position encoding is one of them. And as you can see on the right-hand side, input and then input embedding, and then the next step is we need to add like positional encoding. So what is position encoding then? So as we discussed before, self-attention mechanism captures dependency and context. So in short, date normally refers to time, but when we know there in the sentence there's another word, fruit, it captures the context from fruit, and in this case, date most likely refer to the edible fruit instead of the time. However, in language, order matters. So this is the most classical example that you're gonna see everywhere. So here's why order matters. So even though she did not win the award, she was satisfied. That is one sentence. The other almost identical sentences, even though she did win the award, she was not satisfied. So they have the same character, same word, but the order is different and the meaning is completely different. So other than the context, the previous mechanism that captures context, obviously we need a way to know the position information, right? And previously we know the relative position based on like maybe the index of the word embedding, but that's not enough. We need something similar to a embedding. So that is the position encoding here. So a naive way is, okay, we need another embedding for position. And the most naive approach is we just put the position of the word as the embedding, right? For example, the first word E0 stands for the word embedding for the first word. And P0 stands for the position encoding for the first word. And because it's the first word, the index is 0, so P0 will be all 0. Similarly, E1 will be P1 will be all ones, and Pn will be all n's. Like, will this work? This is not working, since like large n's will skew all the embeddings. Like you can imagine if the sentence is like 100 word long, then like En plus Pn, that is the new input for the nth position. The embedding will be a lot larger than E0 plus P0, so the result will all be skewed. So we need the following properties then, right? We need to bound min and max value, and we still want it to be able to differentiate like the position info, like whether it's the real position or the encoded position. So let's try something else. What if we include like normalization in it, right? So we normalize it by the first P0 is all 0, P1 is like 1 over n. That means for Pn it's 1, right? In this case, all the values is between 0 and 1. So this won't work perfectly either. Like there are some caveats, like encoding for the same word combination will have different encodings. The sentence length is different. Here's an example. So there is two sentence. I am a dad, which is 4 characters long, 4 word long, and there is I am Martin, that is 3 words long. And in these two sentences, the sub-sentence I am, those position encoding will be different, and we don't want that. We want it to be like ideally to be the same. So we need another property, which is the encoding ideally it's not dependent on the length of the sentence. So what's the actual like solution here? The proposed solution is actually very smart. So as you can see, this is the two formula of the position encoding. POS is the position of the word, and it's so for first word is P0, for second is P1, this is typo, and then P2, P4, P2, P3. So D is the dimension of the embedding for the words. In this case, our word embedding have 5 dimensions, and 2i it means the even indices of position encoding, like within those D dimensions. So 0, 2, 4, 2i plus 1 is the odd indices. And you can, for the even values, you just use the first sine formula. For odd position, you use the second one, cosine value. And just to clarify, all the values I put here is fake. Just put random numbers. So now we combine the semantic embedding, which is E0, E1, E2, E3, and the position encoding, which is the P0, P1, P2, P3. We combine those and we have a positionally aware semantic embeddings, which is what we want. So now we have the perfect input for the transformer model. So then we are ready to dive deeper into what actually happens in the transformer model and how attention mechanism is actually using these semantic, positionally aware semantic embeddings. And I'm gonna dive deeper into those topics in the following episodes. Before those episodes, I also wanna provide some intuition to this position encoding. So this is the intuition, and this is this graph on the right hand side. It's for even indices. 2i equals to 0, 2i equals to 2, 2i equals to 4, and they have they have similar sign graph, but they have different frequencies, right? And they have those properties that we want. They have bound min and max values, 1 and -1, and they're able to differentiate encoded position info. Like for example, even let's say for I equals to 2i equals to 0, there's like 2 points, a 2-word position, they have the same value for I equals to 0. If you take a look and see like for 2i equals to 2 and 2i equals to 4, the value is going to be different. So in this way, the encoded position, the position encoding is actually different, even if let's say for I equals to 0, they're the same. They have the same value. For the other two i's, they're going to have different values. So this algorithm is able to differentiate encoded position. And yeah, we know they're not dependent on the length of the sentence. So for I am Martin and I am a dad, the I am like common prefix will have the same encoded position encoding. So this is the intuition. Hope it helps a little. And the next episode, I'm going to talk about how to use this positionally aware input in the attention mechanism. Hope this is helpful. Thank you, everyone.